So this is the fifth lecture of ISI question solving. So today's question is, let me show you what is the question. So the question was this one, fifth question. So A and B a sequence of Borel measurable set of 0, 1. That means what is Borel measurable set? Borel measurable set is sigma algebra generated by open intervals of 0 and 1. What are open interval of 0 and 1? Open intervals of 0 and 1 is open intervals of R intersection closed interval 0 and 1, right? And what is sigma algebra? Sigma algebra is you take any set. Sigma algebra means you take any two set from the sigma algebra A and B, and their finite union is there, that is algebra, and complement is there. So together this is called algebra. But sigma algebra is countable union. If you take countable collection of sets from that collection, so you have countable union also belonging to the set, and together with the complement you can conclude that using De Morgan's law, intersection of countable intersection also inside. So countable union, countable intersection, and under complement the set is closed. So that is Borel, that is sigma algebra. And if you generate from a set sigma algebra, that is just a intersection of all the sigma algebra containing that set. That is the smallest sigma algebra. So in that way you can say Borel's measurable set is the sigma algebra generated by the open intervals of 0, 1. Okay. Now as you know that every open interval can be measured by the Lebesgue measure, and Lebesgue measure is computable under countable intersection and complement. So that's why the Borel measurable sets are simply our measurable sets, right? So we can apply the measure lambda on the sets, and that's why we can apply lambda of an, and lambda of an is equal to 1. It is given for all n. Now we have to prove the intersection of all the an is dense in 0, 1. Okay, so that is the question. So it is intuitively like each an is spread through all the 0, 1, so it doesn't give a space. Meaning if you take any point from 0, 1 and want to create an open interval around it, that is a vacuum, and in that vacuum there must be at least a point of an, otherwise the measure of the an cannot be 1, right? Because measure of the an would be the measure of 0, 1 minus that open interval, and that cannot be 1 because open interval must have a length. So in a sense we have to prove that intersection of all an's measure is also equal to 1. So if we can prove that, that is easy to prove again from that intuitive logic, or it is same logic, it is mathematical logic also. You can say that yes, this is dense. So let us prove that intersection of all n is measure is 1. So okay, so our goal is to prove lambda of intersection of all an is equal to 1. This is our claim. Okay. As you can see, intersection of all n can be also measurable, is also measurable, right? Because we can apply measure on a sigma algebra, right? So intersection, countable intersection of measurable space, measurable sets also measurable, so we can find the measure. So this is our claim that we can find 1. This is in that way how we extend the modulus, I mean length of an interval. So countable intersection in a way using the continuity from above we can find using the property. So whatever, these are the things that we can find a value associated to countable intersection, or in a procedure in which we can say this is measurable, means we can find its length, right? Or we can associate. Measurable means it is in the domain of the function. That means the function is from the function lambda is from a subset of a power set, right, which is called as a sigma. This is a subset of a power set of some x to some r positive union, let's say 0. So this is the set where this is the set called measurable set. That means each element, if we associate some positive real number that doesn't violate the properties of the other sets interacting with, meaning non-measurable sets is a sense that if we assign them some real number, then using the property of the measurable sets with countable union or countable intersection, that using disjoint union, we can write it as a sum. But in that way, if we write them as a countable union, disjoint union of measurable sets, and then add, that will violate the property of them that we assign them, right? So in such a way, so in a sense, how they interact with, that would be violated. So that is examples how we can construct a non-measurable set. So the idea of the non-measurability is just to हम ऐसे assign कर दे उसके ऊपर एक कोई भी नंबर में भी जीरो या फिर कोई भी और नॉन नेगेटिव नंबर, so that would give us a contradiction under the countable union or countable intersection, that this is not possible. Okay, so this is the idea. I mean, assigning them a real number would violate the same assignment on other. I mean, the same set of rules in which we will assign into the other, in keeping the property that under countable, disjoint countable union, we can have summation of them, and for intersection, that will be the smallest one, or countability from below or countability from above. In that way, the function's properties would be violated if we assign them. So yeah, that is the idea of finding non-measurable. And obviously non-measurability completely depends on how we start the domain. Yeah, so how we start the domain from the smallest set, like here intervals. If we started the function from other sets, other kind of special sets, then obviously the non-measurability property would be, non-measurable sets would be different. Maybe in some different measure, the non-measurable sets would be the intervals. It is always possible. Okay, so that is the definition how we started our assignment, and that's how the domain becomes restricted. Instead of every set, domain becomes only some sets generated from the intervals and some other kind of sets. So yeah, that is the whole sigma algebra basically. Okay, so now this is our claim, how we can do this. So let us try. So we can prove the semi-additivity, and that's how we can do it, right? Using the positiveness, we can prove the semi-additivity and all, and this would be right. And look, each of our an is measure 1, so an complement is nothing but 1 minus an, because measure of 0 1 and but this is 0, so these are 0, so this is less than equal to 0, but that is also positive. So in a way we get that this one is 0, and that is nothing but what? In 1 minus lambda of an is 0, meaning what we needed is proved, right? That proves our claim, and these are all basically using the properties of the measure, and I have just given you the overview. You can skip them if you don't want or you already know it. This is the deep concepts, whatever. So basic concept basically. Now this is one. Now if you have the same idea intuitively or mathematically, if you think let's if possible let this is not dense, then there exists some x belonging to 0 1 which does not belonging to the this. That means there exists a ball, I mean an interval, that means a epsilon positive, such that x minus epsilon to x plus epsilon intersection is phi. That means x minus epsilon to x plus epsilon is completely inside this complement, but we have found the complement measure is 0, but from here the measure of this interval is less than equal to measure of this, which is 0, but that is a contradiction because this is 2 epsilon is less than equal to 0 means epsilon is 0. This is a contradiction, right? So that is the set should be intersection of n should be our 0 1. That proves it. So thank you.